Okay, number 6 on our review. What we have next is one of our polynomial inequalities. We need to figure out where is this polynomial less than 0. We're going to start off by finding the zeros. Okay, we start off kind of like we would if it were an equation rather than an inequality. And when we have 4 terms like this, what we want to think about is factoring by grouping. So we want to ask ourselves, what do these first 2 terms have in common? What do these last 2 terms have in common? See what we end up with. So from the first 2 terms, I can factor out an x squared. What's left behind is 3x minus 2. From the second 2 terms, they do both share a 3, but we can go even higher than that. They both share a 9. And since this leading term is negative, I want to factor out a negative 9. That gives me then negative 27 divided by negative 9 and positive 18 divided by negative 9. And great news, factoring by grouping works because these 2 expressions match. That is now our GCF, so we pull it out front. And what's left behind then is x squared minus 9. And then we can factor one more time because that leaves us with a difference of 2 squares. So we get an x minus 3 and an x plus 3. So here's our factored polynomial inequality. Next up, we want to find the zeros or the boundary points. So we're going to take each one of those factors and set them equal to 0. Here we get x is 2/3. Here we get an x is positive 3. And here we get an x is negative 3. Notice what I did not do is take this sign and just transfer it to each one of these. That is not how we solve these. These are the points where our polynomial could be changing signs. These are our boundary points. So what we're going to do with those is next we're going to put them on a number line in order from smallest to biggest. Doesn't have to be to scale. I wouldn't label any other points, just those boundary points. They are the important points. And those points split our number line up into 4 sections or 4 intervals. We need to look at each one of these intervals to figure out the sign of our polynomial in each section of the number line. So I'm going to put my factors over here on the side. And I'm going to choose some test values. I need something smaller than negative 3. How about negative 10? Something between negative 3 and 2/3. I always like 0 because that simplifies calculations a lot of times. Something between 2/3 and 3. I could use 1, or I could use 2, or I could use 2.5 if I wanted. Something bigger than 3, about 10 again. Okay, I take each one of these test values and plug it into the factor I have over here on the side. So when I put negative 10 in for x, I get 3 times negative 10 is negative 30 minus 2, which is definitely a negative number. Negative 10 minus 3 is a negative number, and negative 10 plus 3 is also a negative number. I do the same for x equals 0. 0 minus 2 is negative, 0 minus 3 is negative, and 0 plus 3 is positive. Plug in 1, I get 3 minus 2, 1 minus 3, and 1 plus 3. And then finally plug in 10, and it turns out that they all end up being positive. So what I really care about is what happens when I multiply those signs in a column. So in this first interval, we have our factors are all negative. So a negative times a negative times a negative means my polynomial is negative in that interval. A negative times a negative is a positive times another positive stays positive. So my polynomial is positive in that interval. Next up, we have one negative, so that one becomes negative. All positives, so that one is positive. These are the signs that determine my answer. Remember, what we were looking for was, where is this polynomial less than 0? Less than 0 would be our negative columns. Go up that column and we can see the interval that gives us that result. So this first interval is from negative infinity to negative 3. Any x value in that range will give us a negative polynomial result, less than 0. Also, it's negative in this third column, which look at our number line, that goes from 2/3 to 3. So also any x values between x equals 2/3 and x equals 3 will also give me a negative result. And you do have to show some kind of sign chart to justify your answer. You can't just guess at the intervals for this. Make sure you know how to show your work. Number 7, domain. We need to find the domain of this function. Remember, domain is the set of values where our function is defined, okay? Meaning we could do those calculations on our calculator and not get an error, okay? So here we have two things we need to think about. We need to think about the square root. Okay, the square root function is something we have to consider when we're talking about domain, because we cannot take the square root of a negative number, which means we have to grab whatever's under that radical symbol and make sure that is greater than or equal to 0. If it's not greater than or equal to 0, we will get an error, okay? So we need, that's our first part of our domain. We get 2x greater than or equal to negative 30, divide by 2. So for sure, x has got to be greater than or equal to negative 15. If it's not, we're going to get an error when we try to type this in on our calculator. Okay, that's one piece of our domain. But this function has something else going on too. It's also a rational function, meaning it has a denominator with variables in it, okay? We cannot ever allow the bottom of a fraction to be 0, because in mathematics, division by 0 is undefined. So the other thing we need to look for here is we want to make sure that x squared plus 3x minus 28 is not equal to 0. That's the other piece of our domain. So to figure this out, we are going to need to factor x squared, factors into x times x. 28, let's see, we could have 1 times 28, or 2 times 14, or 4 times 7. 4 times 7 is going to get me that 3x I need in the middle. And to get a positive 3x, I need plus 7 and minus 4. Double check. Yes, that does give me that negative 28. So with these two factors, I get two values I need to exclude from my domain. X can't be 4, because that would give me a 0 denominator. And also x cannot be negative 7, because that would give me a 0 denominator. So I have all the pieces of the puzzle. Now I have to put them together into interval notation. If you can see right away how to do that, just do it. That's great. If you need a visual of what's going on here, it might help to put it on a number line. Sometimes I have students try to do a sign chart for this. You don't need a sign chart, just a number line, okay? So if we're going to kick out 4, can't be 4, so I put a little open circle there. We're going to kick out negative 7, can't be negative 7. And it also has to be greater than or equal to negative 15. So negative 15, let's say, is down here. Close circle because of the equal to. So it could be between negative 15 and negative 7, cannot be 7. It could be between negative 7 and 4, can't be 4, and it could be bigger than 4. So this number line, the shaded areas, show me my intervals I need to write for my final answer. So from negative 15 to 7, not including 7. From 7 to 4, not including 4. And from 4 to infinity. There is our interval notation for our domain. Number 8, we move into transformations. It asks us to find the equation for the function that is finally graphed after the following transformations are applied to y equals x squared in the order listed. So here they gave us a parent function. Make sure we use that when we write our equation, okay? I like to do these transformations sort of step by step to build up to my final answer. So I'm going to start with this. If it's first, just shifted 2 units to the right. What that's going to look like is f of x equals x minus 2 squared. That's a horizontal. Oh, that's to the, yeah, that's to the right. Yes, that's a horizontal shift to the right by 2. There's my first step. Then reflected about the x-axis, reflecting over the x-axis, that's like a vertical reflection. So that's when we have the negative sign out front, separate from the squared part of our equation. And then finally, we need to shift that down 4 units. So f of x equals negative x minus 2 squared. Down 4 units is a minus 4 at the end. So there is our transformed equation. Make sure you don't just write the expression f of x equals and then your equation. Number 9, same kind of problem, just a different parent function. So this time we are starting with square root of x. And let's apply the transformations in order here. So reflect about the y-axis. Over the y-axis, that's a horizontal reflection. So instead of the negative going out front, it goes right there inside the square root symbol. Stretched vertically by a factor of 2. A vertical stretch means we are multiplying by 2 outside of the function. And finally, a shift up 5 units. So we have our stretch, we have our reflection, and then shifting it up 5 is a plus 5 at the end. There is our function. Still within transformations, now we want to find the domain of this function, and then we want to sketch the graph. So let's start with the domain. Similar to our last domain question, we do have a square root here. So like I said before, we have to make sure this expression under the radical is not negative, because if it were negative, it would be undefined. So x minus 3 has to be greater than or equal to 0. We add that 3, means x greater than or equal to 3. Inequality notation, interval notation. It doesn't say which one we have to do here, so I'd say either is okay. Sketch the graph. So let's talk about what's going on with this graph. This graph is got the minus 3 inside there, so that is shifted 3 units to the right. It's got this negative sign out here, so that is a vertical reflection or reflection over the x-axis. And we've got this minus 4 at the end, which is a shift of down 4. So depending on how familiar you are with the parent function, I'm just going to kind of sketch it in here. The square root function, remember, it has an endpoint. It only continues on in the one direction. It has the endpoint at the other direction. So if we do right by 3, if I'm going to scoot that over, let's make that blue. 1, 2, 3. It would then look like this. Okay, then it reflects over the x-axis, so it would flip down to look something like this. And then shift down by 4. 1, 2, 3, 4. 2. So our final graph would look like this. Now, if you don't know the parent function well enough to draw it precisely like you need to, these problems usually say make sure you show at least 3 points. I would recommend building a t-table. And we're going to use our information about our transformations to choose our x value wisely, or the information about the domain to choose our x value wisely. Don't put 0 in for x, because right here it says that x has got to be greater than or equal to 3. So plug 3 in there, grab your calculator, do the calculations. You're going to get 0 minus 4, which is negative 4. Plug a 4 in there, see what we get. We get negative 1 minus 4, which is negative 5. So this was that first point we found, and then 4, negative 5. There's our second point. Then you could use 5, but you might want to pick x values wisely so that you can actually take the square root and get an even number. That's a little easier to graph if we do that. So if we put a 7 in there, 7 minus 3 is 4. Square root of 4 is 2. Negative 2 minus 4 is negative 6. Again, you can do that on your calculator, what I just did. So that does give me those 3 exact points for our graph.